get that every day. And so what was going on? So as I understand it, what was going on was that this was the first flight of the Ariane 5 launcher, and it reused some of the guidance software from Ariane 4. That's fine. Good. Tested code should reuse it. But the launch profile for Ariane 5 went sideways a bit more, on purpose, than the Ariane 5 launch. And as a result, one of the sideways values in the guidance control software overflowed. Bad. And hence the guidance software decided that something bad was going wrong, and in order to not land rockets on people's heads, it kindly blew itself up. Okay. So that's the spectacular. Sometimes they go wrong in insidious ways. And you people probably know much more about that than me. Very insidious ways, exploited by bad people to our detriment. And they go wrong in insidious ways, exploited by our kindly governments for our protection. And there are many, many, many different causes of these things, but many of these causes are completely trivial. You know, you have one line of code in the wrong place, something like that. Right? So that's very, very bad. And you're all conscious of how bad that is. But from my point of view, this is as nothing with the real disaster that we have been facing and continue to face. Right? The real disaster is the enormous waste of human life and energy and effort and emotion dealing with these crap machines that we build. Right? And it's hard to quantify that. I did a little experiment a couple of months ago. I Googled up Android problem and Windows problem and got about 300 million hits for each. Right? Somehow indicative of the amount of wrongness. You know? So this should seem kind of familiar to you. If you think back to when you were young, maybe back in the 19th century, when you were young. And what were you doing then, as a community of hackers and makers and builders? Well, this was the full-on industrial revolution. You were building stuff. You were building beautiful bridges of cast iron and stone, with numerous arches and pillars. And every so often, they would fall down. I believe someone miscalculated the wind loading. And we would build magical steam engines to whisk us away. And every so often, they would blow up. And that kind of thing, as you may have noticed in the last 100 years, blow up. That kind of thing doesn't happen very often anymore. Right? We have pretty good civil and mechanical engineering. And what does it mean to have good civil and mechanical engineering? It means that we know enough thermodynamics and material science and quality control management and all of that kind of thing to model our designs before we build them and predict how they're going to behave pretty well, you know, with pretty high confidence. Right? I see an optimization in this talk. For computer science, for computing systems, we can predict with 100% certainty that they will not work. Time for lunch. But it's not a very satisfying answer, really. So why is it so hard? Let me discuss a couple of the reasons why computing is tricky. In some sense, trickier than steam engines. Right? The first reason is that there is just too much code. Right? So this is one of the more scary graphs I found on the internet recently. This is a measure of code in hundreds of millions of lines. Each of these blocks, I think, is 10 million lines of code. And in the little letters, you might not be able to see, we have Android and the Large Hadron Collider and Windows Vista and Facebook, US Army Future Combat System, Mac OS, and software in a high-end car. I'm flying home. So that's a bit of a problem. Really, we're never going to get that right. Then, there's too much legacy complexity there, right? Really too much. So as right-minded, pure-minded people, you might think that software and hardware should be architected beautifully with regular structure, a bit like a Mies van der Rohe skyscraper or something, clean. Okay, you know that's not realistic, right? You might expect a bit of baroqueness. You might expect maybe something more like this. You know, it's a bit twiddly, but it hangs together, it's still got structure, still works. But then you stop and you think, and you realize that software and hardware is built by very smart people, and usually in big groups, and subject to a whole assortment of rather intense commercial pressure and related open source pressure, and using the best components and tools that they know and that they like. And the best management that human beings can arrange. So we end up with something spectacularly ingenious. And you can see here, if you look closely, you can see all the parts. This was just a found picture from the internet. But you can see there's a bunch of, transparent sort of silicon-like stuff down here. Let's say that's our hardware. And over here, I see a C compiler with all of its phases. And these bottles, that's the file system, I reckon. And there's a TCP stack in here somewhere. And there's a piece that belongs to the NSA, obviously. And up here, there's a JavaScript engine and a TLS stack and a web browser. And then perched at the top is the software that most people use to talk to their banks. It's just insane. Right? And then we have to look at how we build these pieces. Right? So we build them fundamentally by a process of trial and error. Right? Just occasionally, we write some specifications in text, and then we write some code, and maybe we write a few ad hoc tests, and then we test and fix until the thing is marketable, and then we test and fix and extend until the thing is no longer marketable, and then we keep on using until we can't anymore. Right? So the fundamental process that we're using to develop these systems is trial and error by exploring particular execution paths of the code on particular inputs. But, you know this, but I want to highlight, there are too many. The number of execution paths scales, typically, at least exponentially with the size of the code. And the number of states scales exponentially with the size of the data that you're dealing with. And the number of possible inputs is also shockingly large. There is no way that we can do this. And we should perhaps stop deluding ourselves that there is. And then the most fundamental reason that computers are hard is that they are too discrete. Right? If you take a bridge, or, I don't know, a chair or something, where's something slightly bendable, you take a chair and you exert a bit more force on it than it's used to. I'm not very strong. And it bends a bit. It deforms continuously. If you take a bridge and you tighten up one of the bolts a bit too much, or you underspecify one of the girders by 10%, occasionally you will reach a point of catastrophic failure, but usually it will just be a little bit weaker, or a little bit stronger, or a little bit wibbly. Right? But computer systems, you change a bit, sometimes it doesn't make any difference, but disturbingly often, or you change a line of code, as in some of those bugs that we were talking about, the whole thing becomes broken. Right? So it's quite different from that traditional engineering. It's really different. Okay, so A New Dawn, this thing is titled. What can we do? What might we do? So I'm going to talk about several different possibilities. Right? One thing, we can do more of the stuff which is traditionally called software engineering. It's not really engineering in my book, but some of it's good. Right? I mean, it's useful. You know, we can do more testing and have more assertions in our code and better management, maybe, and all that kind of stuff. We can do all that. We should do all that, but it's not going to make a very big change. Right? It's not addressing any of those root causes of the problem. What else could we do? So as an academic computer scientist, I've devoted several years of my life to working in the area of programming languages. And I look at the programming languages used out there in the world today. It's just disgusting. It's shocking. The reasons that languages become popular and built into our shared infrastructure, the reasons for that have almost nothing to do with how well those languages are designed, and in fact, whether they are designed at all. Right? So, I didn't really want to get too much hate mail after this talk, so I'm going to try and avoid naming particular languages as much as I can, but I encourage you to think away as I speak and imagine the examples. Right? No, that was, I didn't want to get much hate mail. Oh, sorry. So at the very least, we could use programming languages based on ideas from the 1970s instead of the 1960s. I mean, really, come on. Right? Back in 67 or 69 or whatever, we had BCPL and C, and only a couple of years later, we had languages that guaranteed type and memory safety and enforcement of abstraction boundaries and gave us rich mechanisms for programming so that we could say what we mean and not futz about with 23 million pointers, about 1% of which were completely wrong. Right? So for any particular, in the context of any particular project or any particular existing legacy infrastructure, there may be very good reasons why one just can't make a switch. Right? But for us collectively, there is no excuse. Right? It's just wretched. It's completely bonkers. And then the other thing that you see as a programming language researcher is that, to make another analogy, it looks as if anyone who was capable of driving a car considered themselves an expert on car design. Right? There is, in fact, a rather well-established subject of programming language design, and we know how to specify completely precisely, mathematically precisely, not just the syntax like we had in these BNF grammars from the 1960s and still have, but also the behavior of these things. We know how to specify the operational semantics and the type systems, and we know how to do mathematical proofs that our language designs are self-consistent, that they do guarantee good properties of arbitrary well-typed programs that you write. Right? So we can do this now. We can do it, if we have to, post hoc, and people are doing this for JavaScript and C and, God help them, PHP and other such languages. But even better, we can do it at design time. And if you do this at design time, you see the structure. The act of writing that specification forces you to consider all the cases and all the interactions between features. You can still get it wrong, but you get it wrong in more interesting ways. Right? So people are starting to do this now. So I think there was a talk on the first day of this by Hannes and David, who are building system software in maybe not the bestest language you could possibly imagine, but something which compared with C is as manna from heaven. Right? And Anil Madhavapedi and his colleagues in Cambridge have been working hard to build system software in at least moderately modern languages, and it works. Sometimes you have to use C, but surprisingly often you really don't. So I teach, as my introducer said, in the University of Cambridge, and in fact I teach semantics. And one of my fears is that I will accidentally let someone out into the world who will accidentally, over a weekend, find themselves inventing a little scripting language which will accidentally take over the world and become popular. And I won't have explained to them what they have to do, or even that there is a subject they have to understand. And if you want to understand it, there's lots of stuff you can look at. Okay. Let's go to the uppermost extreme. If we want software and hardware that actually works, we should prove it correct. Right? So this is something which academics, especially in the domain of labeled formal methods in the 70s and 80s, they've been pushing this, promoting this as an idea and a promise and an exhortation for decades. Right? Why don't we just prove our programs correct? And for some of those decades, it wasn't really plausible. I remember back when I was considerably younger, it was a big thing to prove that if you took a linked list and reversed it twice, you got back the same thing. Right? That was hard then. But now, well, we can't do this for the Linux kernel, let's say, but we can, surprisingly often, do this. Right? And I just give you a couple of the examples of sort of modern-day, state-of-the-art academic verification projects. Right? People have verified compilers all the way from C-like languages down to assembly, or from ML-like languages, higher-order functional imperative languages, all the way down to binary models of how x86 behaves. Right? And people have verified LLVM optimization passes. There's verified software fault isolation, which I believe goes faster than the original non-verified form. Win for them. There's a verified hypervisor from the Nicta group in Australia, right? Verified secure hypervisor with proofs of security properties. There's any amount of work verifying crypto protocols, sometimes with respect to assumptions, but I think reasonable assumptions, on what the underlying mathematics is giving you. Right? So we can do this. I maybe have to explain a bit what I mean by prove. To some computery people, I proved it works means I tested it a little bit. In extremis, it compiled. To a program analysis person, you might run some sophisticated tool, but written in untrusted code and possibly doing approximate and maybe unsound analysis, and you might find an absence of certain kinds of bugs. That's tremendously useful. It's not what we would really call prove. I mean, nor would they, to be fair. Scientists generally don't use the word because they know they're not doing it. Right? They're doing controlled experiments, which gives them, information for or against some hypothesis. Mathematicians write proofs. Right? And you probably did that when you were young. And those proofs are careful mathematical arguments, usually written on paper with pencils. And their aim is to convince a human being that if that mathematician was really nailed up against the wall and pushed, they could expand that into a completely detailed proof. But what we have in computing, we don't have the rich mathematical structure that these people are working with. We have a tremendous amount of ad hoc and stupid detail mixed in with a smidgen of rich mathematical structure. Right? And we have hundreds of millions of lines of code. So this is just not going to cut it. And if we want to say the word prove ever, then the only thing which is legitimate really is to do honest program proof. And that means you need to have some system that machine checks that your proof is actually a proof. And sometimes we also have machines that will sort of help and sort of hinder that process. Right? And there's a variety of these systems, Coq and Hall 4 and Isabelle Hall and what have you. that one can go and look up. Right? So using these systems, we can prove non-trivial facts about these. Not necessarily that they do what you want them to do, but that they meet the precise specification that we've written down. We can do that. But it's tricky. Right? So these projects, these are, by academic standards, all quite big. This is something like, I don't know, 10 people for a few years or something. By industry scale, maybe not that big. By your scale, maybe not that big. But still a lot of work for a research group to do. And quite high-end work. It can take literally a few years to become really fluent in using these tools. And there isn't, as yet, a sort of an open-source collaborative movement doing this kind of stuff. Maybe it's the time to start. Maybe in 5 years, 10 years. Don't know. If you want a challenge, there's a challenge. But it's really quite hard. Right? It's not something that one can quite put forward credibly as a solution for all software and hardware development. Right? So that leads me to like an intermediate point. That should have been a 4 there. What can we do which improves the quality of our systems, which injects some mathematical rigor, but which is less work, which is kind of easy? Right? And what we can do is take some of these interfaces and be precise about what they are. And initially, we have to do that after the fact. We have to reverse engineer good specs of existing stuff. But then we can use the same techniques to make much cleaner and better tested and things which are easier to test in the future. That's the idea. So my colleagues and I have been doing this kind of stuff for the last quite a few years, and I just want to give you just two little vignettes, just to sort of show you how it goes. So I can't give you much detail, and this is obviously joint work with a whole bunch of very smart and good people, some of which I name here. Right? So this is not me, this is a whole community effort. So I'm going to talk for a little bit about the behavior of multiprocessors, so at that hardware interface. And I'm going to talk a tiny little bit about the behavior of the TCP and Sockets API, right? Network protocols. So, and there'll be some similarities and some differences between these two things. So multiprocessors. You probably want your computers to go fast. Most people do. Right? And it's an obvious idea to glom together, because processors don't go that fast, let's glom together a bunch of processors and make them all talk to the same shared memory. This is not a new idea. It goes back at least to 1962, when the Burroughs D825 had, I think, 2 processors talking to a single shared memory. It had outstanding features, including truly modular hardware with parallel processing throughout, and some things do not change very much. The complement of compiling languages was to be expanded. Right. 1962, so that'll be 52 years ago. Dearie me. Okay, now how do these things behave? So let me show some code, right? It's a hacker conference, there should be code. Let me show you 2 example programs. And these will both be programs with 2 threads, and they'll be acting on 2 shared variables, x and y. Right? And in the initial state, x and y are both 0. So, first program, on this thread we write x and then we read y, and over here we write y and then we read x. Right? And these are operating in an interleaving concurrency, you might think. So there's no synchronization between those threads, so we might interleave them. We might run all of thread 0 before all of thread 1, or all of thread 1 before all of thread 0, or they might be like mixed in like that, or like that, or like that, or like that. Right? There's 6 possible ways of interleaving 2 lists of 2 things. And in all of those ways, you never see in the same execution that this reads from the initial state and this reads from the initial state. Right? You never see that. So you might expect, and you might assume in your code that these are the possible outcomes. So what happens if you were to actually run that code on my laptop in a particular test harness? Well, okay, you see occasionally they're quite well synchronized and they both read the other guy's write. Sorry, big call. They both read the other guy's write. And quite often one thread comes completely before the other. But sometimes they both see 0. Huh. Rats. Well, that's interesting. Let me show you another program. So now, thread naught writes some stuff. Maybe it writes a big bunch of data, maybe multi-word data. And then it writes, let's say that's a flag, announcing to some other thread that that data is ready to go now. And the other thread busy waits, reading that value until it gets 1, till it sees the flag, and then it reads the data. So you might want, as a programmer, you might want a guarantee that this read will always see the data that you have initialized. Okay, that would be like a message passing kind of an idiom. So what happens if you run that? Well, on the x86 processors that we've tested, you always see that value. Good. Right? This is a decent coding idiom on x86, apparently. On ARM and IBM Power processors, however, you see sometimes you just ignore the value written and you read the initial state. Okay, so this is not a good message passing idiom, right? So what's going on? Well, this behavior, it might be surprising. Okay? And when you see surprising behavior in hardware, you have two choices. Either it's a bug in the hardware, and we have found a number of bugs in hardware. It's very rewarding. Or it's a bug in your expectation. Or it's a bug in your test harness. So what you do is you walk along and you walk up to your friendly processor architect in IBM or ARM or x86 land, and we have worked with all of these people, and you ask them, is this a bug? And a processor architect is a person who has the authority to decide whether some behavior is intended or is a bug. That's what they do, essentially. And for these, they say, oh, we meant it to be like that. No question. We meant it to be like that. That's perfectly proper. We have, because you and everybody else wanted their computers to go fast, we, as processor designers, have introduced all manner of sophisticated optimizations, which if you were running sequential code, you would never notice. But if you start running fancy concurrent code like this, fancy concurrent code that isn't just trivially locked, you can notice. So this is intentional behavior. And if you want to write that code, like a mutual exclusion algorithm or a message passing algorithm or something, then you need to insert special instructions, memory barrier instructions. And so you go away and you say, oh, what do they do? And you look up in the vendor documentation. And you get stuff like this. I'll read it out. For any applicable pair AB, the memory barrier ensures that A will be performed with respect to any processor or mechanism to the extent required by the associated memory coherence required attributes before B is performed with respect to that processor or mechanism. A includes all applicable storage access by any such processor or mechanism that have been performed with respect to B1 before the memory barrier is created. B includes all applicable storage access by any such processor or mechanism that are performed after a load instruction executed by that processor or mechanism has returned the value stored by store that is in B. Hands up if you understand what that means. Hands up if you think that if you thought about it and read the rest of the book, you would understand, or you could understand what that means. Hands up the people who think that we're doomed forever. So I'm sorry to the first few groups, but the last ones are right. So this looks like it's really intricate and really carefully thought out stuff. And we thought that for a while, and we spent literally years trying to make precise mathematical models that give precise meaning to all of these words. But actually, it can't be done. All right? So what do you have to do in that circumstance? You have to go away and you have to invent some kind of a model. All right? And this is a really fundamental problem that on the one hand, we develop our software by this trial and error process, but on the other hand, at points like this, we have these loose specifications, supposedly, that have to cover all manner of behavior of many generations of processes that might all behave the same way, written just in text. And we tell people they should write to the spec. But the only way they have of developing their code or their hardware, usually, is to run it and run particular executions on the particular hardware implementations that they have, whose relationship to the spec is very elusive. Yeah? We can't use those thick books that you get, or those quite weighty PDFs that you get these days from the processor vendors, to test programs. You can't feed a program into that thick book and get output out. And you can't test processor implementations, and you can't prove anything, and you can't even communicate between human beings. Right? So these things really, they don't exist. So what can we do? Well, the best we can do at this point in time is a bit of empirical science. Right? So we can invent some model off the top of our head, trying to describe just the programmer visible behavior, not the internal structure. And we can make a tool, because that's not prose now. Now it's stuff, it's real mathematics, and we can turn that into code and execute it. We can make tools that take programs and calculate, small programs, the set of all the behaviors allowed by that model. And then we can compare those sets of behaviors against the experimental observations, and you might have to fix the model, and you might find hardware bugs. And then, well, the model also has to make sense to the architect, so you can discuss with the architects whether it matches what they intend and what their intuition is, and then you can also prove some other facts about it to give a bit more assurance. And then, because you probably got this wrong the first couple of times, you can go back. All right? And this results, or has resulted in models which are not guaranteed to be correct, but they are effectively the de facto standard for understanding the concurrency behavior of these things. And various people use them. And just to give you a tiny snippet, I'm going to have to speed up a bit, a tiny snippet of what the model looks like. Right? It's basically just an abstract machine. It's got some stuff for the threads that handles the programmer visible speculative execution, and some stuff for the storage subsystem that handles the fact that in these architectures, memory writes can be propagated to different threads at different times. Right? And that model has a state, which is just a collection of some sets and lists and partial orders and a few other things, which I won't talk about. And it has some transitions. Right? In any state, there might be several possible transitions. So this is just a sample. I'm not going to explain all of this, but when you want to propagate a write to another thread, there are some preconditions that you have to satisfy, and then there's an action. It's not amazingly complicated, really. But this is text, but it's very precisely written text, and it has a great advantage that you can go through these bullet points with your friendly architect and say, is this what you mean? And they can think about it and say yes or no. Right? But for the actual definition, that's in mathematics, but it's mathematics which is quite close to code. I mean, it's terribly close to pure functional code without side effects. And just to give you an idea, this is some of it, and those are 3 of those conditions in the real, honest, true version. Then we can take this mathematics, and because it's in a particular style, we can compile this into actually OCaml, and then OCaml bytecode, and then we can run that for batch jobs, but then you can compile that OCaml bytecode to JavaScript, and glue on a user interface, and stick it into a browser, and then you have a web interface that lets people explore this rather intricate model. And that's also a necessary part of validating that it makes sense. Okay, this is not rocket science. You've missed the talk for rocket science, I'm sorry. All we're doing here is specifying the intended behavior of a system. Okay, it's not very technical, but it's unusual. And we happen to be doing it in this mathematical language, but you could use, in fact, almost any language, so long as you understand what you're doing. And what you have to understand is that you're writing something which is not an implementation. It is something which, given some observed behavior, some arbitrary observed behavior, will be able to decide if it's allowed, if you want it to be allowed or not. Right? It has to be executable as a test oracle. The key question for getting this to work is to understand how much non-determinism or loose specification there is in the system that you're working with. Right? So if everything is completely deterministic, you can write a reference implementation in the cleanest language of your choice and just compare the output of that and the output of your real thing. Right? But if there's more non-determinism, then you can't do that. I'm going to have to abbreviate this a little tiny bit. Right? So for TCP, network protocols, there is more non-determinism. You know what TCP is, yes? Protocol gives you sort of reliable connections, assuming that the world is made of good people. Right? You look at the standards for TCP, and they're the same kind of ribbly text from the 1980s. And you look at the implementations, and they're a ghastly mess. Right? And you try and understand the relationship between the two of them, and you can't, because the standard, again, is not a definition. It doesn't define, in all circumstances, what behavior is allowed and what isn't. Right? So again, we had to make up a specification, in the first instance, just of this host, a single endpoint, and observing its sockets, API calls and returns, and its behavior on the wire. Right? And when you've decided, and a few internal debug events, when you've decided what to observe, then an observation is just a trace. It's just a list of those events, and you have to be able to ask your spec, is that list admissible or not? But there's a lot of non-determinism, variation between implementations, variation within an implementation. And that's internal, a lot of it. It's not announced in the API or on the wire, maybe until much later. When the implementation picks some new, window size or something, you can't tell until quite a lot later in the trace what it's picked. And that makes the job of checking whether a trace is admissible by the spec much harder than it has to be. And if you had designed the TCP protocol and those implementations to be testable in this very discriminating way, back in the 1980s when you were designing TCP protocol, it would be much easier. Right? And for new protocols, one should make sure that you're doing this in this particular way. I don't think I want to talk about that slide. That's just one of the rules of that specification. But the key fact about that spec is that, well, we handle the real protocols for arbitrary inputs, but it's structured not just for this executability as a test oracle, but it's structured for clarity, not performance, which is scarcely ever what anyone ever does. Right? So it's a whole new kind of thing. Yeah? And the testing is very discriminating. So we found all manner of amusing and bizarre bugs, which I think I don't have time to talk about. Right? Okay, so I've described three kinds of things that we might do. Right? First thing, oh, for goodness sake. I mean, it's just a no-brainer. Just do it already. Everybody, all of you. This middle zone is a very interesting zone as far as I'm concerned. Right? It's kind of a place where we can get a very good benefit for not that much effort. Right? We can do it, if necessary, post hoc. We can also do it, and even better, at design time. We have to do this in a way that makes our specifications executable as test oracles, and another thing that enables is completely random testing. When you've got a test oracle, you can just feed in random goop. This is fuzzing, but better fuzzing. Feed in random goop and check at every point whether what the behavior that you're getting is allowed or not. Right? And then they're written for clarity, not for performance. And that means you can see what you're doing. Right? You can see the complexity. If you go ahead and you add some feature to your protocol or your programming language or whatever, and you're working just with text specifications, then you can't see the interactions. You just chuck in a couple of paragraphs and you think for a few minutes. Right? And if you're lucky, you make an implementation. Right? But if you're writing a spec that has to cover all the cases like this, the act of doing that encourages you to think, or helps you think about the excess complexity. Right? And you might think, oh, that's too complex. I'm being silly. I'll make it simpler. And it has to be usable for proof. Right? So this, I think, also is pretty much a no-brainer. And it doesn't require great technical, mathematical skill either. Right? Lots of people can do this. And then there's option 3, best option, full-on formal verification of the key components. Right? And that is now also within reach. Right? You can imagine secure systems made using actual verified compilers and verified hypervisors with possibly verified TLS stacks, and you can imagine making things out of those, or making those and then making things out of those. Right? And maybe one should be thinking about that. Maybe not appropriate for everything. If you are writing Word, you would not wish to do these things. Probably you're not. But for this key infrastructure that we really depend on, that we trust, even though it's not trustworthy, we have to do this. Is this a new dawn? I wonder if there's anyone standing next to a light switch that can dim them for me. I didn't ask them beforehand, so... if you think back, the last 70-odd years, we started building computers in around 1940. It's been pretty dark from the point of view of rigorous, solid, reliable engineering, stuff that is actually trustworthy. Pretty dark, I would say. Maybe, just maybe, there's a tiny smidgen of light coming through the doors, and we start to have a little bit of a clue, and we start to get reusable models of processor architectures and programming languages and network protocols and what have you. It's just the beginnings of the analog of that thermodynamics and material science and quality control management and what have you that we have for mechanical engineering. Right? And we've got no choice. If we don't, the next 75 years is going to be a lot worse. You can just imagine, right? So I went to this, as I'm sure many of you did, this great talk on some Apple bootloader exploit yesterday, which was relying on some feature that had been introduced in the early 80s and was still present. Right? And you can imagine, in 100 years from now, you can imagine as long as human civilization endures, the x86 architecture and the sockets API and all of this stuff, it will be embedded in some monumental, ghastly stack of virtualization layers forever. So, I'd like to thank especially all of my colleagues that have been working with me or not with me in these directions. I'd like to thank our generous funders who support this stuff. I'd like to thank you for your attention, and I exhort you, sort it out.
Thank you very much, Peter, for those interesting insights to our programming. We have now time for a Q&A. So those people who have to leave the room, please do so quietly and as fast as possible so we can go on and hear what the questions are. So we start with microphone 4, please.
Hello. Thanks for the talk. And my question is, if you got an oracle of the software behavior which can translate every possible input to a correct output, how can this be less complex and error-prone than a reference implementation?
So good question. So the first point is that this oracle doesn't have to produce the outputs. It only has to check that the inputs and the outputs match up. And then the second point is that in general, it might have to have much of the same complexity, but by writing it to be clear as opposed to be fast, you may adopt a completely different structure. Right? So the structure of our TCP spec is organized by the behavior that you see for particular transitions. The structure of a real implementation has fast path code and lots of complicated intertwined branching and all manner of excess complexity, of implementation complexity, if you will.
Thanks.
So microphone 3, please.
I wanted to ask you what's your thought about programming by manipulating the abstract syntax tree directly so as to not allow incompilable programs because of some, like you're missing a semicolon or something like that. What's your thoughts on that?
So that's, in the grand scheme of things, I think that's not a very big deal. Right? So there's people have worked on structured editors for Lordy knows how many years. It's not a big deal because it's very easy for a compiler to detect that kind of thing. Right? And even more, it's very easy for a compiler of a sensibly designed language to detect type errors, even for a very sophisticated type system. So I don't think that's not, I mean, some people might find it helpful, but I don't think it's getting to the heart of the matter.
Thanks.
So we got some questions from our signal angels from the IRC.
Yes, there's one question. It's about the repository for Isabelle and whole proofs. It's there should be on SourceForge, and you said there are no open source repositories. What about them?
Not quite sure what the question is, really. So there's a repository of Isabelle formal proofs, which is the archive of formal proofs, it's called. I didn't really mean to say that there are no open source repositories, and in fact I don't know under what conditions most of those proofs are licensed. They probably are open, but there isn't an open source community building these things. Right? It's still pretty much an academic pursuit.
Microphone 2, please.
Yeah, hello. Thanks again for your talk. I just want to add something that you didn't address. And that's that we actually need more good studies in software engineering. We often hear a lot of experts and also very well-known computer scientists say things like, well, we just need to do functional programming and OOP is bad and stuff like that, which I think there's a lot of truth to it, but we actually need studies where we test these kinds of claims that we make. Because when you look at other fields, which you also did compare to, like medicine, if somebody comes around and is well known and says like things like homeopathy works, we don't believe them. We do trials, we do good trials, and there's a lot of myths out there, like or not well tested things, like hire the best programmers. They're 100 times more productive. Do use static type systems and stuff like that. And we actually need to verify that this is actually true, that this helps, and not just.
Okay, so in the grand scheme of things, arguably you're right. I mean, in the grandest scheme of things, computer science is actually a branch of psychology, or really of sociology. Right? We are trying to understand how large groups of people can combine to make things which are insanely complicated. Now, would it be good if we had, solid evidence that programming in this language was better than programming in that language? Well, yes, but it's staggeringly difficult and expensive to do honest experiments of that nature. I mean, they're scarcely ever done, right? You might do, little experiments on little groups of students, but it's really difficult. Right? And then some of these things which I'm saying, when one is familiar with the different possible options, are just blindingly obvious. Right? I mean, there are reasons why these people are using OCaml for their system programming. Right? It's not, homeopathy is right, but homeopathy is wrong, which is the kind of argument being put forward.
So, question from microphone 5, please.
So where are you using ECC memory for your testing? Up here?
When you say up here, there's a bit of ambiguity. Thank you. Say again?
So where are you using ECC memory for the testing you showed about the results of the multi-threaded results due to memory barriers and memory reorderings?
Well.
Okay, but even if you were or you were not, the point I want to make is that you can expect to have about 1 bit flip each minute in a modern computer system that might completely change what your software is doing. So perhaps we also have to look in ways how we can work if something goes wrong at the very low level, so that we kind of have a check against our specification on a more higher level of our software. So it is valuable to do good engineering on the low levels, but still I think we will not solve the problems of computation and computer engineering just by proving things in the mathematical domain, because computers are physical entities. They have errors and so on, and we really have to deal with them as well.
So it's certainly true that there are such random errors. In fact, I would put the point that I would argue that you have to be able to model the physics well enough, and you have to be able to model the statistics of those errors well enough. So that's a different kind of mathematics, and it's certainly valuable and necessary. But if you look at even the statistic you just quoted, is that the main cause why systems go wrong? Except possibly for space hardware? No. Right? So, important? Yes. The most important thing that we should be paying our attention to? I don't really think so.
Microphone 6, please.
Hi. I really think that what you're proposing to specify and verify more key components would be a valuable addition. But how do you make sure that your specification actually matches the behavior that you want to have?
So as I described, we do, as partial validation of those specifications, we do a lot of testing against the implementations, against a range of existing implementations. That's one source of validation. Another source of validation is that you talk to the architects and the designers. You want the internal structure to match their intent. You want it to be comprehensible to them. Another kind of validation that we do is prove properties about them. So we prove, for example, that you can correctly compile from C11 concurrency, from a mathematical model of that, to IBM Power concurrency. And that proof, that kind of proof, gives you a bit more assurance in both. So none of this is giving you a total guarantee. You certainly don't claim a total guarantee, but it gives you pretty good levels of assurance by normal standards.
Mic 4.
Yes, thanks again. You proposed random in tests, and with my expertise, it's very annoying if you have tests where the outcome is sometimes a failure, and you want to have reproducible tests, to fix a bug. So how do we bring these aspects to test more variety in data and to have it reproducible together?
Well, if, as I was mentioning for the TCP thing, the problem with reproducibility is exactly this internal non-determinism, right? The system makes some scheduling choice or what have you, and you can't see what it is, or the checker can't see what it is. So one way to do that is to really design the protocols in a different way, to expose that non-determinism. The other fact about this kind of general purpose specification as test oracle idea is that in some sense it doesn't have to be reproducible. Right? The specification is giving you a yes-no answer for an arbitrary test, and that means you can use arbitrary tests. Figuring out the root causes of the differences afterwards may be tricky, but you can use them for assurance.
So we now got time for 2 more questions. Microphone 1, please.
Hi, thanks for a great talk. What you've described seems to be a middle ground between a full-on formal verification and more practical testing, like in between. So where do you see in the future where formal verifications will go? Will it converge to the middle, or whether it will still be there just to verify something that's more well specified?
Well, so the progress of sort of the whole subject of formal verification in general, if you look at that over the last, 10 years or so, it's been really amazing compared with what we could do in the 80s and 90s and early 2000s, right? So the scope of things, the scale of things for which it is becoming feasible to do verification is getting bigger. And I think that will continue. I don't know when you might see a completely verified Tor client, let's say, but that's not inconceivable now. And 20 years ago, that would have been completely inconceivable. Right? So that is expanding, and at the same time, I hope that we'll see more of this interface test oracle-based specification. And these, when you're doing formal verification of a piece of the system, you have to have these interfaces already defined, right? So these two fit very well together.